Hi, welcome to Lecture 6.2, Graphs of Exponential Functions. Now, in 6.1, we learned all about what an exponential function was, how it behaves. We looked at special exponential functions that have to do with the base e, and also known as the natural base. And we looked at compound interest formulas. So in 6.2, we're going to take that knowledge of the exponential function and look at it from a visual perspective. In other words, we're going to put it onto a graph and see how those characteristics translate into the Cartesian plane. Okay, so general word about graphing exponential functions. Now, we have already graphed one, and we actually graphed the one that's right here on the screen for us, which is f of x equals base 2 raised to the x power. And we're told to observe how the input values are increasing additively by 1, and what happens in our f of x is that we're actually increasing multiplicatively. We're multiplying by the base one more time to get to the next value. So, and actually I should be drawing arrows because all those things are not equal. So here we're adding 1. So as our input increases additively, our output increases multiplicatively. So whenever you have an output increasing multiplicatively, you've got this particular function, exponential function. Let me take a sip of coffee real quick. It's early. Okay, so notice in the graph of 2 to the x that all the output values are positive. This is an increasing function, and it increases without bound. It also, as your input value decreases, it begins to approach the horizontal asymptote that is the x-axis. So let me just draw that in for you. We do have a horizontal axis at y equals 0. Okay. Now let's contrast this with 1/2 raised to the x power. So we're still increasing additively in our input values. But in our output values, we are multiplying by the base, and that's 1/2. So our values are actually getting smaller. This becomes a decreasing function. And you just take half of the 1/4. So half of 8 is 4. Half of 4 is 2. Half of 2 is 1. Half of 1 is 1/2. Half of half is 1/4. Half of 1/4 is 1/8, and so on. So as x increases, these values begin to approach that horizontal asymptote of y equals 0, And as x decreases, the input grows, the output grows without bound. So it has basically, when you look at 2 to the x, which I'll put on this graph here so we can see them together. I'll do this in green. Look at them together. So I have -3 1/8, -2 1/4, -1 1/2. I'm sorry, -1, yeah, 1/2, 0 1, 1 2, 2 4, 3 8, so it appears that when you graph a base raised to a variable, and you graph that base's reciprocal raised to that same variable, that it appears to reflect across the y-axis. Okay, so a general note. So this is just going to kind of summarize everything you're seeing with exponential functions, whether that base is greater than 1 or whether it's between 0 and 1. So these are one-to-one functions, which means that their inverse will also be a function, and that's what we're going to talk about in 6.3 and 6.4, is the inverse of f of x equals a times b to the x power. Horizontal asymptote at y equals 0. The domain is negative infinity to positive infinity range. You go from that horizontal asymptote out into positive infinity. No x-intercepts. Notice that both go through the point 0, 1. So when your base is greater than 1, you're increasing, and when your base is less than 1, you are decreasing. Okay, so we are asked to graph this exponential function in the form of b to the x power. So we're going to create a table of points. We go ahead and get that set up. So we have an x and an f of x. It says to plot at least 3 points from the table, including 0, 1. I'm going to put 0, 1 in the center and do -2, -1, 0, 1, and 2. I'm going to do 5 points. Okay, so f of -2 says to raise 0.25 to the -2nd power. Now that's 1/4, so actually I prefer it in a fraction state because I can do it in my head if I have fractions, but since it's given as decimals, I'm going to put it in my calculator. So 0.25 raised to the -2nd power, and I get +16. Just to show you how that happened, I am going to do that one with fractions. So if we have f of -2, 0.25 is 1/4, so that's 1/4 raised to the -2nd power. That's 1 to the -2nd over 4 to the -2nd. I'm going to switch both positions so that my exponents become positive. which is 16 over 1, or just 16. So that's how that came out like that. All right. So 0.25 raised to the negative first power is 4. Anything raised to the 0 power is 1. 0.25 raised to the first power is 0.25. And 0.25 squared is 0.0625. Okay, I'm ready to put this onto the graph. So I have negative 2, 16. Negative 1, 4. 0, 1. 1.25. Ooh, that's almost already on our horizontal asymptote. And 2, 0.627. It's really down there. So this decreases rapidly. And then it's going to follow that horizontal asymptote. I actually crossed over, but you knew what I meant to do because you know what asymptotes are. So it's my horizontal asymptote at y equals 0. Because I have not shifted up or down. Notice my b value is between 0 and 1. So I have a decreasing function here. It says to state the domain and range. Domain for any exponential function is negative infinity to positive infinity. The range, if I have not done any vertical shifting, will always be 0 through positive infinity. 0 non-inclusive, by the way. And I have a horizontal asymptote at y equals 0. Okay, so now notice we have a b that is greater than 1. So we should expect an increasing function here. I'm going to do the same thing, set up an xy table. X, f of x. 1, 2, 3, 4. I'm going to have 0, 1 in the center. Negative 2, negative 1, 1, 2. 4 to the negative second power is 1/16. 4 to the negative first is 1/4. Anything to the 0 is 1. 4 to the first is 4. 4 squared is 16. Okay, I'm going to put that onto the graph. Negative 2, 1/16. Negative 1, 1/4. 0, 1. 1, 4. And we're going to shoot way up. 2/16. That one wasn't as bad as a 0.25, huh? Still not great, but not nearly as bad. Here's my horizontal asymptote at y equals 0. We have a domain. Nothing's changed. Negative infinity to positive infinity. And a range from 0 through positive infinity. Okay, transformations. This is where it gets a little more interesting. However, we already know all about transformations, so this should not be a shock to you. To vertically translate an exponential function, you're going to add or subtract a value depending on which direction you want to go on the outside of the function. So here, by the way, my orange function here is just good old 2 to the x. So it's in that parent or toolkit position. I have my horizontal asymptote at y equals 0. If I add 3 to the outside of the function, meaning after I've already raised that value to that input, that variable input, then I shift this thing up 3. So instead of going through the 0.01, I add 3 to that and go through the 0.04. I also add 3 to my horizontal asymptote. My horizontal asymptote is now y equals 3. And then if I subtract that same value on the outside of the function, I'm going to shift down 3. So I go from the 0.01 to 0, -2. I'm still increasing because my base is greater than 1. And I've shifted my horizontal asymptote down 3. Also good to note how the range changes here. When we vertically shift, that's a y value characteristic. So that's going to change our y values. My range shifts with my horizontal asymptote. And you can see that right there where I've pointed out on the screen for you. Okay, and then we have horizontal shifting. So translating left or right. This happens on the inside of the function. And don't forget that when we translate left or right, it's inside inverse. So when I add 3 to the actual variable before it's run through the function, then it's actually going to shift this thing to the left 3. So I move from 0, 1 to -3, 1. So that is -3, 1. The horizontal asymptote does not change, meaning my range does not change either. Okay, and then if I subtract 3, the inverse of what you'd think, it's going to shift it to the right 3. So I go from that 0.01 to 3.1. Once again, horizontal asymptote and range have not changed. Okay, so general notes on shifting of the parent function b to the x. For any constant c and d, we have b raised to the x plus c on the outside of the function plus d, and that shifts the parent function vertically d units in the same direction as the sign of b, horizontally c units in the opposite direction of the sign of c, so inside inverse. And that's on the inside of the function that we're talking about. The y-intercept becomes b raised to the c power plus d for our y value. And notice that the 0 is still there for the x because it would not be a y-intercept if it did not. Pardon me. The horizontal asymptote becomes y equals d, the range becomes d to positive infinity, and the domain remains negative infinity to positive infinity. So let's go ahead and look at doing this. Okay, so how to. First thing we want to do is get the asymptote out of the way. That's easily identified by identifying D. Then we're going to identify our shifts as the opposite of C and D. So that's our horizontal and our vertical shift. And that is where that point 0, 1 is going to shift to. And then we shift the graph of b to the x left C units. If C is positive, right C units. Okay, so we know that. Up and down with a D, and then we state the domain and range. So we'll do this in the table, and I'll show you how to do those transformations within an XY table. So we're going to start with our parent function. We'll call this g of x equals 2 to the x power, which we're already very familiar with this particular table. So -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. Okay, so let's go ahead and place some things on the graph. We have our horizontal asymptote, which has been shifted up 3. So our D is equal to 3. So our horizontal asymptote is right here. We also have a horizontal shift. Get a different color. The opposite of -1, which is +1. So our shifting is to the right 1 and up 3. That point 0, 1 shifts to the point. It shifts to the right 1 and up 3. So that point shifts to 1, 4. So it went from 0, 1, we went right 1, and then up 3 to get to that point. I'm just taking that excess off there. All right. So to move into our transformed f of x table, we have f of x equal to 2 to the x minus 1 plus 3. So we're going to start out with the x values from our parent form of the function. And each of those get shifted to the right 1, right 1, right 1, right 1, right 1. I'm getting that from right there. And that leaves me with new x values of -1, 0, 1, 2, and 3. And then I take my original y values, 1/4, 1/2, 1, 2, and 4. And I'm going to shift each of those up 3, up 3, up 3, up 3, and up 3. And that gives me the new y values. This is 3.25, So 3.5, 4, 5, 7. Okay, so I have the point, -1, 3.25. It's about right here. Then I have 0, 3.5. There's my 0.14, 2, 5, 3, 7. So we know we're increasing because our base is greater than 1. And we can state y equals 3 as our asymptote. And then we have a domain of -infinity to +infinity, and our range, since we have translated vertically, we have to consider that everything's been moved up. So that is from 3 through +infinity. Okay, using your calculator to solve exponential equations. This is actually a very handy skill to have because you can do this with any equation. Any type of equation you can want, you can use your graphing calculator to actually solve it. And here's what you do. You take each side of the equal sign and you give it its own function. So in this case, for 42 equals 1.2 times 5 raised to the x power plus 2.8. In my graphing calculator, I go to the y1 feature, or the y equals feature, and I put in y1 equals 42. That's going to be a horizontal line that goes through 42. And then I take the other side of the equation and put that in as another function. So 1.2 times 5 to the x power plus 2.8. So what's going to happen is that y2 function is some increasing exponential function. And then I have a horizontal line at 42. And where these two functions intersect at that x value, that is where they are equal. So that's what you're trying to figure out, is when are these things equal? So you just need to figure out what the x value at that intersection is. So that's what I'm going to do here. I'm going to first go to y equals, and I do y1 is 42. Y2 is 1.2 times 5 raised to the x power plus 2.8. And then I go to my graph, and my window's way off. So here's a little tip for you. When you graph something and you don't really see what you're trying to see, go to your zoom feature. That's your function key in the top center, and arrow all the way down to zoom fit. Zoom fit is going to try to find the place on your graph that gives you the most information. And let's see. Okay, I see an exponential. I'm waiting for my horizontal. I don't know if it's going to show my horizontal line or not. It's not. So I've got to go and adjust my window. So I'm going to adjust the y-axis. I need my y-axis at the very least to show 42. So I'm going to go up to 50 on my y-axis and see if I get a better picture. Yeah. So I think I can show this to you on Desmos as well. Yes, I can. Let's go out and take a look. Let me first make sure that my screen is on Desmos. Yes. Okay. Okay, so I have y equals 42. And then I have my other function, and actually let me zoom out on this a little bit so we can get a good picture. Zoom in a little. Okay. I think it'll graph a horizontal line. No, I don't know. And maybe not. And then we have the other part of our function, 1.2 times 5 raised to the x power, and then plus 2.8. Okay, I'm not sure why this is not graphing a horizontal line for us. Okay, well, you can imagine a horizontal line coming through at y equals 42. So right here, whenever, see, 42, output of 42. I don't know if it'll let me get right on it or not. Not quite. So I'm going to have to go to my graphing calculator to calculate that point. Okay, so to calculate the point on your graphing calculator, let's go back to our whiteboard. Okay, so you've got your graph. You see your two functions there on the same screen, and you see where they cross. To calculate that intersection, you're going to press the second key and then the trace function at the top. That's going to be your calculate menu. So second and trace, and you're going to choose 5, which is your intercept function. And it's going to ask you first curve. You want to just arrow your cursor that's blinking onto one of the functions and hit enter. So I put my cursor on y equals 42 and I'm hitting enter. And then it says second curve. You just want to make sure it's on the other function and hit enter. And then it says to guess. Don't worry about guessing. Just hit enter. And it'll take you right to the intersection. And I'm getting my intersection point as 2.1661943 and 42. Okay, so it says to round to the nearest thousandth. If I look at my x value, the thousandth place is right here. I'm going to look next door. That means these two functions are equal when x is equal to 2.166, rounded to the thousandth place. So that's how you could use your calculator to solve equations. You just put it in two chunks on either side of the equal sign and see where they intersect. That x value where they intersect is solving for the x value that makes those two things equal. Okay, so same thing for the next one. I'm going to have in this case, a y1 of 4 and a y2 of 7.85 times 1.15 raised to the x power minus 2.27. So I'm just going to put those in now. I'm going to go back to my y equals, and y1 equals 4, and y sub 2 equals 7.85 times 1.15 raised to the x power minus 2.27. Okay, so I do need to see, well, no, I don't need to see negative values because they cross above the asymptote. That makes sense. All right, then second and trace is my calculate menu. Go down to calculate the intersection. First curve, enter. Second curve, enter. Guess, don't worry. Just hit enter. And I am getting the intersection point as negative 1.608. And of course, a y value of 4, since that's where my horizontal line is. So in this case, my x is equal to negative 1.608. Okay, stretching and compressing. We also have this transformation to discuss. And lucky you, it's the same transformation with stretching and compressing that we've been studying since the very first test worth of material. So notice that when you multiply on the outside of the function by a value greater than 1, this stretches the function vertically. So it pulls it vertically quicker. And when you multiply by a value that is between 0 and 1 on the outside of the function, it compresses it down. And actually, they made these colors to be very confusing. This is our 2 to the x. So it's the orange on the other side right here. They should have let 2 to the x be the same color in both of these. And then our compressed function here. So that's a 1/3. So that's between 0 and 1. And this is a 3, which is greater than 1. So same old stretch and compress. Don't forget that for compression, vertical compression, it needs to be between 0 and 1. The sign has nothing to do with stretch and compress. So if I did -3, it's still going to be stretched vertically, but then we're moving into reflection when we start changing the sign, which we'll talk about in a moment. So notice in the description down here that they use the absolute value. So they're taking the sign out of consideration because that's reflection. It's just that value of that factor that you're multiplying with that determines stretch or compress. Okay, so here we have 4 to the x, which has been compressed vertically. So the first thing I'm going to do is start with a parent function, 4 to the x, I'm actually going to put this onto the graph so that you can compare it since we're looking at stretch and compress. And we've already created an XY table for this particular function. So that's 1/16, 1/4, 1, 4, and 16. So I am going to put this on the graph. -2, 1/16, -1, 1/4, 0, 1, 1/4, 2/16. We have our horizontal asymptote. We go through 0, 1, and then we shoot straight up. We should expect this transform function to increase at a slower pace. So it's going to be more compressed towards the x-axis. So f of x equals 1/2 times 4 to the x. Nothing changes with our input values. I have made no changes in the horizontal direction, or I have not compressed or stretched horizontally. So my x values remain the exact same as they were for my parent or my toolkit function. -2, -1, 0, 1, and 2. Now what has happened with my output values is that I take my output from my parent function and I'm going to multiply each of them by half. So I'm just writing down my original parent function output values, and then I'm going to come back and multiply each of those by 1/2. So it should make sense that since each of those values are getting halved, that they're going to be smaller. So it's going to compress it down towards the x-axis. So I get new output values of 1/32, 1/8, 1/2, 2, and 8. So -2, 1/32, -1, 1/8, 0, 1/2, 1, 2, and 2, 8. So you can see that new function doesn't rise quite as quickly as our parent function 4 to the x did. Okay, reflection. So just like we've studied since the very first test, when you change the sign on the outside of the function, so not on the variable, not on the input variable, but on the outside of the function, as noted here, you're going to reflect across the x-axis. And when you put a negative on the variable, you're going to reflect across the y-axis. So, take a look up at the top. We have our parent function that's luckily blue in both of these cases, 2 to the x. Going through that point, 0, 1. When I place a negative or multiply by -1 on the outside of the function, it's going to reflect it across the x-axis. So I'm now going through the point 0, -1. Changes my y values, or changes the sign. Changes the sign of my y values. Okay? And if I multiply by -1 with the variable before I've run it through the function, it changes my x values, changes the sign of my x values. Notice this still goes through 0, 1 because 0 doesn't have a sign. Changes sign of x values. So where I normally have 1, 2, let me point this out, where I normally have 1, 2 on this function, I have -1, and then my output has to be, we have to go by the rules of having that negative exponent, so it halves it there. No, I'm sorry, -1. I went to the wrong function. I was like, that doesn't make sense. Okay, so we have the point. Let me start over on this one. We have the point 1, 2 that shows up on our parent function. And then we also, on our transform function, have the point -1, 2. So it changes the sign of the x values when you do that reflecting over the y-axis. Okay, so find the graph of the equation g of x that reflects 1/4 x about the y-axis, or sorry, the x-axis. So if we're reflecting over the x-axis, that negative comes on the outside of the function. So our g of x is going to be -1/4 to the x power. Okay, so let's start with our parent. F of x equals 1/4 x. We have 0, 1, -2, 16, -1, 4, 1, 1/4, 2, 1/16. Our b value is between 0 and 1, so we have a decreasing function here. I'm going to go ahead and put this onto the graph. -2, 16, just for comparison purposes, -1/4, 0, 1, 1, 1/4, 2, 1/16. So we're decreasing rapidly here. And we are going to reflect across the x-axis, and I put the wrong graph on here to graph this reflection. Give me 2 seconds to get a better graph. I need to see, there we go. I'm just going out to Desmos and grabbing a new blank graph. Give me a moment. And I'll be right back with you after I can grab a picture of this. All right. Okay, let's come back here. And give ourselves a fresh graph to work with. Morphing it a little bit there to fit it. Okay, do over. Let me, oh no, what happened? It doesn't want to group it as a background. I have to group things as a background so they don't move around when I write on them on the screen. So I'm going to have to be careful with this and just write on top of it. All right, now I'm going to put our parent onto the graph. So -2, 16, let's see, 10, 12, 14, 16, -2 is right here. Now this one's not going to look as steep as the other one because you can see I've morphed my graph. So I'm counting by 0.2 on the x-axis, and I'm counting by 2s on the y-axis. So it's going to look a little morphed. -1, 4, 0, 1, 1, 1, 4. Oops, that's not 1. 1, 1, 4, 2, 1, 16. So we have this. Still decreasing. All right. So what we know is that our reflection over the x-axis right here with that negative is going to change the sign of all of our y values. That's the only thing that changes. So I still have -2, -1, 0, 1, and 2. Now I have -16, -4, -1, -1/4, and -1/16. So -2, -16 here. -1, -4, 0, 1, 1, -1/4, 2, -1/16. So this thing comes like this. All right, so horizontal asymptote is the same for both of these. It also happens to be their line of reflection. So the asymptote is y equals 0. The domain for my new function is still -infinity to +infinity, but my range changes. It flips over, comes from -infinity and goes all the way up to, but does not include 0. And now let's look at one that flips over the y-axis. So our f of x is 1.25 to the x power. And our g of x, if we want it to reflect over the y-axis, we need to make our input value negative. 1.25 to the negative x power. So that's going to change the sign of all of our x values. Let's go ahead and do our parent first. So -2. All right, I'm going to need my calculator for this because y'all know I don't work in decimals in my head very well. 1.25 raised to the -2nd power is 0.64. 1.25 raised to the -1st power is 0.8. And then 1.25 and 1.25 squared is 1.5625. Okay, so I can actually get a new graph for this as well and not have to see so much in my y values. Let me change this graph here. I want to go from -2 to 2 in our y values. Okay, let me grab this. And place it here. Make it a little smaller so it'll fit. Okay. All right, so I'm going to go ahead and put my parent onto the graph. So I have -2, 0.64, so that's a little more than a half. Maybe about right here. -1.8. 0, 1, 1, 1.25, and 2, 1.5. So approaching, we're going up. You're only seeing a very tiny portion of this graph, so it's not going to look as close to an exponential as you're used to seeing. Okay. And for my transformed function, the only thing that changes is the sign of the input value. So I have +2, 0.64, +1, 0.8, 0, 1, -1, 1.25, and -2, 1.5625. So we're looking for reflection over the y-axis now. So +2, +0.64. Right about here. +1.8. 0, 1, -1, 1.25, -2, 1.56. Okay, so this comes like this, and then it's going to go towards that horizontal asymptote. We have not translated vertically, so the horizontal asymptote is still the y-axis. I'm sorry, the x-axis, which is y = 0. We have a domain of -infinity to +infinity, and a range Range hasn't changed from 0 through positive infinity. Okay, so this is just a summary page of your translations. And I just stuck that in there purely for your studying benefit. So this is everything I just went through, so I'm not going to go through this page. And then finally, can you write the equation for a function given characteristics of it? Sure we can. So if we're told that our parent function is e to the x, we want to vertically stretch by a factor of 2, reflect across the y-axis, and then shift up 4 units. Okay, so we start out with our parent function, e to the x power. And I'll color code each of these transformations. So we're going to vertically stretch by a factor of 2. Vertical stretching happens on the outside of the function. And then we will reflect across the y-axis, and y-axis reflection happens on the variable. And then, finally, we will shift up 4 units. That happens on the outside. There's your function. Same thing here. We'll start out with e to the x. This time, we want to vertically compress by 1/3. Reflect across the x-axis. That happens on the outside of the function. And then shift down 2, -2. There we go. I hope this was helpful for you.